From a distance, the Panama Canal looks like a shortcut through land. A ship enters from the Atlantic, crosses Panama, and eventually comes out into the Pacific. Simple enough, but that is not actually what happens. A ship entering the Panama Canal does not stay at sea level. It is physically lifted about 26 meters into the air, carried across the middle of Panama on a freshwater lake, and then lowered back down to the ocean on the other side. That means a cargo ship weighing tens of thousands of tons can enter one side of Panama at sea level, rise roughly 8 stories without using a crane, travel through mountains that once blocked its path, and then descend back to sea level before continuing across the world. And somehow, the system doing all of this is powered mostly by gravity. No giant elevator lifts the ship. No pumps have to hoist the entire vessel upward. Instead, enormous chambers fill with water around the ship until the ship simply floats higher. That sounds straightforward until you realize the Panama Canal may be moving a vessel longer than several football fields while controlling millions of gallons of water behind gates large enough to hold back an artificial lake. And the reason engineers built it this way comes down to one problem they could not simply dig through. Panama is not flat. The country is crossed by the Central American mountain spine. And when engineers first imagined connecting the Atlantic and Pacific Oceans, the obvious idea was to dig a sea-level canal straight through it. That was essentially the original French plan. Ferdinand de Lesseps had helped build the Suez Canal, which works much more like what people imagine when they hear the word canal. The Mediterranean and Red Sea are connected by a channel that remains close to sea level, so ships can travel from one end to the other without being lifted through major locks. Panama looked like the next logical place to repeat the idea, except Panama was nothing like Egypt. The terrain was mountainous, rainfall was intense, tropical disease devastated the workforce, and one river in particular created a huge problem: the Chagres River. During heavy rain, the Chagres could rise dramatically and dump enormous amounts of water into the construction zone. Building a flat sea-level trench would require not only cutting deeply through the continental divide, but also somehow controlling this powerful river permanently. The French eventually considered switching to a lock canal, but by then, their project was already collapsing. When the United States later took over construction, engineers faced the same fundamental decision: dig all the way down through the mountains, or somehow make the ships go up. The second option sounded stranger, but it solved several problems at once. Instead of fighting the Chagres River, engineers could dam it. That would create an enormous elevated lake across the center of Panama. Ships would then be raised from the ocean to the level of that lake, travel across it, pass through the narrow cut excavated through the mountains, and descend back to sea level. In other words, instead of removing the entire mountain, they would raise the ocean-going ships high enough to travel across it. That decision created the modern Panama Canal. The key to the whole system is Gatun Lake. Gatun Lake sits roughly 26 meters above sea level and forms a major portion of the canal's route. To reach it from the Atlantic, a ship approaches the Gatun Locks. Imagine a gigantic concrete staircase, except the steps are filled with water and each one is large enough to hold an ocean-going ship. The original lock chambers are roughly 33.5 meters wide and more than 300 meters long. The ship enters the first chamber at approximately sea level. Huge gates close behind it. At this moment, the ship has gone as far forward as it can. There is a wall of water at a higher level ahead of it and another ocean behind it, so the canal begins changing the water level around the ship. Fresh water from Gatun Lake flows downward through enormous culverts built inside and beneath the lock structure. And here is the part that makes the system so elegant. The water does not need to be pumped upward. It is already above the ship. Gravity sends it downward into the chamber. As water enters, the surface inside the lock rises, and because the ship is floating, it rises with it. The lock is not physically lifting the ship. The water is. Think about putting a toy boat in an empty bathtub and then turning on the faucet. As the water level rises, the boat rises too. The Panama Canal is doing the same thing, except the bathtub is a colossal concrete chamber and the toy boat may be carrying thousands of shipping containers. Once the water inside the first chamber reaches the same level as the next chamber, the gate separating them can open. The ship moves forward. The gate closes again. More water enters. and the ship rises another step. At Gatun, this process is repeated until the ship has climbed to the level of Gatun Lake. Now, the vessel that entered Panama from the Caribbean Sea is floating roughly 26 meters above that sea. That alone is strange enough, but it also explains why the canal could never simply be described as a trench connecting two oceans. For a large section of the journey, the ship is not traveling through an excavated canal at all. It is crossing a lake, and that lake exists because engineers deliberately flooded a huge portion of inland Panama. The route eventually reaches one of the canal's most difficult construction zones, historically known as the Culebra Cut, and later called the Gaillard Cut. This section crosses the Continental Divide. Even after deciding to lift ships above sea level, engineers still had to carve an enormous channel through rock and earth so vessels could pass through the mountains. The cut extends for roughly 13.7 kilometers between the area near Pedro Miguel and Gatun Lake. During construction, gigantic steam shovels, trains, explosives, and thousands of workers removed huge quantities of material, and the mountain kept fighting back. Rain soaked the slopes, earth moved, massive landslides sometimes dumped material back into areas crews had already excavated. There were moments when the amount of earth sliding toward the canal threatened to undo months of work. But once the channel was finally opened, the basic route was complete. Raise the ship, cross the elevated interior, lower the ship. On the Pacific side, the process happens in reverse. The ship enters locks where the water level inside the chamber is initially equal to the elevated canal. The gates close. Then water is allowed to drain out toward the lower side. As the water level drops, the ship drops with it. Again, nothing is physically pushing the vessel downward. Gravity simply removes the water supporting it. The ship moves into the next chamber and drops again until it eventually returns to sea level. The whole trip is basically a controlled staircase made of water, but there is an enormous hidden cost every time this happens. Fresh water. The Panama Canal does not normally use seawater to fill its lock chambers. It depends heavily on fresh water stored in Gatun Lake and the canal watershed. Every time the original locks lower a ship toward the ocean, fresh water eventually leaves the canal system and is discharged toward the sea. That means every ship transit is also, in a sense, a water management operation, and Panama has to supply two completely different things from the same water system. The canal needs water to move ships, but the surrounding population also depends on the watershed for drinking water. That creates a problem during unusually dry periods. If rainfall decreases and Gatun Lake falls too low, the canal cannot simply keep using fresh water without limits. The lake level also affects how deeply ships can sit in the water. A heavily loaded cargo ship extends farther below the surface, something known as its draft. If the canal becomes too shallow, the largest vessels may need to reduce cargo or face draft restrictions. Recent droughts have made this vulnerability much more visible, and the Panama Canal Authority has adopted measures including cross-filling chambers, changing lock schedules, limiting draft when necessary, and using water-saving systems in the expanded locks. And that brings us to another incredible part of the canal. The original locks were designed more than a century ago. Modern ships became so large that many eventually could not fit through them. For decades, shipbuilders even designed vessels around the maximum dimensions of the Panama Canal. Those ships became known as Panamax vessels, but global shipping kept getting bigger. Container ships grew wider, tankers grew larger, and eventually a huge portion of the modern fleet was too large for the original chambers. Panama had two options: watch more ships avoid the canal, or build a much bigger version of the same machine. So it expanded the canal. The expanded waterway opened in 2016 with new locks on both the Atlantic and Pacific sides, allowing much larger Neo-Panamax vessels to pass through. The project also involved excavating more than 150 million cubic meters of material, but simply making gigantic versions of the old locks would create an even bigger water problem. A wider chamber holds more water. Dump that water into the ocean every time a huge ship passes, and each transit could consume an enormous amount of fresh water. So the new locks added another system: water-saving basins. Beside the new lock chambers are enormous reservoirs positioned at different elevations. When a ship needs to be lowered, instead of sending all the fresh water directly out toward the ocean, much of it can be diverted into these basins. When the next ship needs to rise, that stored water can be reused. The Panama Canal Authority says these basins recycle around 60% of the water used during a lockage, so the expanded canal is larger while recovering a significant portion of the water that would otherwise be lost. And all of this still works largely through gravity. The lake sits high, water wants to move downward. Engineers simply control where it goes. That simplicity is one of the reasons the canal has worked for more than a century, but controlling that much water requires enormous gates. The original locks use pairs of giant steel miter gates. When closed, the two leaves meet at an angle pointing toward the higher water level. That shape is important because water pressure actually helps force the gate leaves tightly together. The greater pressure on one side does not simply push the gate open, the geometry transfers much of that force into the surrounding lock walls. Opening the gates requires large mechanical systems. The Panama Canal Authority describes giant bull wheels about 20 feet in diameter connected to electric motors and steel arms that move the gate leaves. The system works almost like the connecting rod on an old steam locomotive. One rotating mechanism moves an enormous gate smoothly through the water. And yet, even with all this machinery, the vessel itself still has to be controlled precisely inside the chamber. A ship entering a traditional Panamax lock may have surprisingly little clearance on either side. There is no room for casually drifting into the concrete wall. Historically, electric locomotives running along the lock walls, commonly called mules, helped control ships using cables while the vessels moved through the original locks. The newer Neo-Panamax locks use tugboats inside the chamber system instead. Either way, the goal is the same. Keep a giant moving object centered while millions of gallons of water rise or fall around it. The ship may look motionless during the lift, but the system underneath is anything but. Valves are opening, water is moving through enormous culverts, levels are changing, gates are holding back huge pressure differences, crews are monitoring clearances, and the entire process has to happen repeatedly, every day for ships traveling in both directions. The canal operates around the clock and serves routes connecting ports across the world. This is why the Panama Canal matters far beyond Panama. Without it, a ship traveling between the east and west coasts of the Americas may need to go thousands of additional miles around South America. The canal removes that enormous detour, but the shortcut only exists because ships are willing to climb. And there is another strange misconception the canal creates. People sometimes imagine the Atlantic Ocean and Pacific Ocean meeting directly inside Panama. They do not. For most of the crossing, ships are traveling through freshwater well above both oceans. A vessel effectively leaves one ocean, enters an artificial inland water system, climbs a hill using locks, crosses the continental divide, then descends into another ocean. The canal is less like a river cut between seas and more like an enormous water-powered conveyor belt for ships. And that explains why the design was so much smarter than trying to dig everything down to sea level. To eliminate the locks entirely, engineers would have needed a vastly deeper excavation through the center of Panama, while still controlling rivers, rainfall, landslides, and enormous amounts of moving water. Instead, they changed the problem. Rather than asking, "How do we remove an entire mountain range?" they asked, "How do we make ships climb over it?" The answer was to build a lake high in the middle of the country and connect it to both oceans with enormous water elevators. More than a century later, the basic concept remains. A cargo ship arrives from the ocean. A gate closes behind it. Freshwater flows into a giant chamber. The ship rises without a crane touching it. It moves forward and rises again until something weighing tens of thousands of tons is floating high above sea level. Then it crosses Panama and the entire process runs backward. The water drains, the ship descends, and eventually it floats out into another ocean as if nothing unusual happened. That is what makes the Panama Canal so impressive. The mountains were never completely removed. The ships were simply lifted over them.